So in this video, we're mostly going to be focused on this figure here from your textbook. And this is just a depiction of all these molecular orbitals that we talked about in the previous video, but without all the drawings of them and pictures of them. We're just listing them in energy order. One thing I'll just point out, and this happens between nitrogen and oxygen, I always forget where the switchover happens, but the ordering of the orbitals switches just these two orbitals here. So this one switches here, this one switches here. It doesn't really have much of an effect on the actual bonding and properties of the orbitals, so that's why I always forget about it. But there's some interactions between the 2s and 2p orbitals that cause this to happen. Don't worry about it. It's not really vital for what we're considering. Okay, so if we look at lithium over here on the left, the lithium dimer, if we have two lithium atoms, they will combine and they'll have two valence electrons that'll get put into this lowest orbital here. And so they'll pair and they'll be in the sigma 2s. So they'll have a bond order of 1, and this will be a diamagnetic molecule. All the electrons are paired. Beryllium, if we go over 1, is non-existent. So our number of bonding and anti-bonding electrons will be balanced out, and this has a bond order of 0, doesn't exist. This is not actually true. I just have to point this out because I worked for one of the one of the professors who actually has studied beryllium dimer when I was a postdoc at Emory, and he published a paper in Science about the beryllium dimer. They made it. It's a very weak bond, but you can actually make a bond between beryllium. It's really interesting. For our purposes, it's non-existent. In reality, it does exist, but hard to make and very easy to break apart. Okay, sorry, I had to include that aside. Right, going on to boron. You can combine two boron atoms, and it'll have a bond order of 1 because now we have two electrons in bonding orbitals, and boron dimer is paramagnetic because we have unpaired electrons. So these two electrons go into degenerate orbitals, the pi orbitals, and we get to this paramagnetic behavior because of unpaired electrons. C2 is a molecule that shows up in flames and soot. Not soot, but flames. It's actually what causes flames to glow, some of the colors they do. And here the electrons are now paired, and so it's diamagnetic, and it forms a double bond. Right, we could draw the Lewis structure for C2. It's going to look something like this. Let's see, we need 8 electrons, so 2, 4, 6, 8. Right, incomplete octet. This is not sort of our usual molecule. It's a very unstable molecule. It doesn't last for a long time, but it makes a double bond. All right, then we can go to nitrogen, which we looked at in the last video, diamagnetic triple bond. And then oxygen, we see unpaired electrons here. Let me get not a white pen. We see our unpaired electrons here. Again, this is a paramagnetic molecule, a double bond. Fluorine, now we have more electrons in our antibonding orbital, so our bond order decreases to 1. This is a diamagnetic molecule. And neon, as far as I know, this is actually true, unlike the beryllium dimer. Neon dimer, two neon atoms stuck together, is going to be non-existent. Again, because all of our bonding and anti-bonding orbitals are filled, they're balancing each other out, and there's no net bonding that happens in this molecule. All right, so that's what's happening across the periodic table as we go from left to right. And I'll just point out as a final note as we finish up talking about molecular orbital theory, this is just a brief introduction. So this idea of molecular orbital theory underlies how we understand bonding in very large molecules as well, not just these small diatomic molecules. It gets a lot more complicated as you get more atoms, but we have computer programs that we use to calculate these molecular orbitals. For diatomics as well as for larger molecules. So this theory is sort of if you really want to get into understanding bonding in atoms, this is the starting point, right? Bonding in molecules, this is the starting point. We can use quantum mechanical tools to actually calculate these orbitals, fill in the electrons, do this sort of thing, and predict the properties. One last thing I'll mention that I mentioned at the beginning is the spectra. And the way we understand the spectra and the colors that we get from these species is thinking about transitions. For example, like in C2 here, transitions between, say, this electron moving up an energy level or up 2 energy levels. That could even happen too, just like with hydrogen. And then maybe that electron falls back down and that emits light. Right? It's these energy levels that are higher than where all the bonds are happening that will lead to the spectra in the visible and ultraviolet range. And so these molecules contribute to things like the aurora borealis. So we have energy coming into the atmosphere, and that causes nitrogen molecules to ionize and also to get excited, and those will glow when that energy is released in the form of light. So that leads to that. That's mentioned in your textbook, and I just thought I'd mention it briefly here too. So that's our brief introduction to molecular orbital theory. There's a lot more we could talk about. We haven't even talked about having different atoms, which you can also do. There's a little bit in your textbooks if you're interested, but we're not going to cover it in class. And I hope this has been interesting. I think this is really cool stuff. Hopefully you could see that. Yeah, we'll talk more in class.